IRODOV problem number 60. In the arrangement of given figure, we have three masses m0, m1, and m2. And moreover, it is given all three have the same mass. And the pulley and the threads are negligible mass, they don't have any masses, and there is no friction in the pulley. Find the acceleration W with which the body m0 comes down and the tension of the thread binding together the bodies m1 and m2. If the coefficient of friction between the bodies and the horizontal surface is k, consider the possible cases. Now we know while solving the problems, we just not focus only on the solution or the formulae. We will bring out the skill for solving the problems. We will enhance our problem solving skills. Same thing we'll do in the project problem. We will go for everything, whatever is present in the problem, and see what triggers us to apply different concepts in the present problem. So basically, we have three masses, and the coefficient of friction is same. Block M1 and the surface has a coefficient of friction K, and block M2 and surface also has a coefficient of friction K, and all the three masses are equal. That is, M0 is equal to M1 is equal to M2. Now, first of all, we have to consider the possible cases. So, first of all, we have to do the analysis whether the motion will happen or not. Okay? And if the motion will happen, then what will be the acceleration of the block? What will be the tensional force in this binding string? And if the motion will not happen, then what will be the tensional force in the binding string? So if we look little bit of fundamental, see, whenever there are two possibilities of the direction of acceleration, we know in the fundamentals we have seen, suppose this is an inclined plane, okay, and we have two blocks. This is your M1 and this is your M2. Okay. Now, suppose I don't know which block will accelerate down and which will accelerate upward. This we don't know. So there are two possibilities of the direction of acceleration. So I can label one of the either direction. So suppose I'm labeling M2 has an acceleration downward. And if M2 has an acceleration downward, then it's obvious that M1 will has an acceleration upward. Okay. Something like this. Now, if in this scenario, when the acceleration can be in either direction, we can label in any possible direction, and the actual direction of A is determined by the algebraic sign of A. So if A comes to be positive, then the actual direction of A will be same as the labeled one. That is, M2 will accelerate downward and M1 will accelerate upward. However, if A comes to be negative, then the actual direction of A will be opposite to the labeled direction of A. Like if A comes to be negative, then M2 will accelerate upward and M1 will accelerate downward. This we have seen in fundamentals. Now see, in the cases where there is only one possible direction of acceleration, like see, suppose we have a table, a rough table, and we have a block, say M1, and there is a pulley, and this is a block, say M2. Okay, and say this is your rough table. So if you see, if I want to know what will be the forces acting on this boundary, of course N will balance M1G, and here gravity will act. On block M2, gravity will act M2G, which will be the pulling force. So gravity will give M2 a tendency to go down, and when M2 will have a tendency to go down, M1 will have a tendency to go towards left. So it will have a tendency to go leftward, and it will have a tendency to go downward. And of course, to oppose this tendency, friction will act on M1 if it's a rough surface. So we don't know whether motion will happen or not, correct? But if motion will happen, if in this case motion will happen, so the only possible direction of acceleration for M2 will be downward, and for M1 it will be leftward. M1 cannot have an acceleration in this case rightward because gravity is acting down. So the only possible direction for M2 to have an acceleration is vertically downward. Okay, so we can label A for M1 towards left and A for M2 vertically downward. So in a case where acceleration can be just in one direction and we label A in that direction, and now suppose after applying Newton's laws, A comes to be greater than 0. If the algebraic sign of A comes to be positive, it means the motion will happen. It means the motion will happen. There will be an accelerated motion. And if suppose A will comes to be, A will come to be less than or equal to 0. A comes to be 0 or negative. So negative A doesn't mean, in this case, don't compare it with that case. In this case, if A comes to be negative, it means the system will remain static. No motion will happen. Okay. So this is the fundamental which we have covered in Newton's law. When there are two possible directions of A, you can label any one direction. If A comes to be positive, actual A will be in that direction. If A comes to be negative, actual A will be opposite to that direction. However, when there is only one possible direction of A, you can label A in that possible direction. If A comes to be positive, there will be an accelerated motion. And if A comes to be negative or 0, there will not be any motion. The system will remain static. Okay. Now, in this problem, the first key point is we have to decide whether the motion will take place or not. First of all, we have to decide whether the motion will take place or not. So the problem says we have two blocks. The problem is saying that we have two blocks. One is M1, there is a string M2, then we have a pulley, and this is M0, correct? And here the coefficient of friction is K, and here also the coefficient of friction is K. So tell me one thing, if at all, the blocks will move, so what will be the possible direction of the acceleration? So in this case, M0 will be acted upon by gravity. So M0 will have a tendency to go down. So the only possible direction of acceleration is both M1 and M2 will have an acceleration towards left, and M0 will have an acceleration vertically downward. No other possible direction of A is possible, correct? No other possible direction of A is possible. So we are labeling A, and all the three blocks will have same magnitude of acceleration. They are connected by a single segment of a string, and the motion is taking place in the direction of the string. So let W be the common magnitude of the acceleration of the three blocks. Okay, we are assuming that the blocks are having some acceleration W. Now it depends whether W will come to be positive or negative, as we have seen in the last skill. Now let us make the FBD. So say the tensional force in this string, it's a pulley, and the string is passing over a frictionless, massless pulley. So this will be T1 and this will be T1, and say here the tensional force is T2. So if I'm making the FBD of M0, I'm making the FBD of M0. So I will have the forces M0G, T1, and the acceleration is W. So I can take a positive axis. That's your choice where you want to take it. Say I'm taking the positive axis vertically downward. So systematic way, we'll say the sigma Fy net force on the y-axis will be M0G minus T1. Ay is W. Now let me apply Newton's second law. Fy is MAY. So I will get the equation M0G minus T1 is what? M0W. Let it be equation number 1. So this you got as the first equation involving T1 and W. Okay, now tell me one thing. Can we make the combined FBD of M1 and M2? The condition for making the combined FBD is that both must have the same acceleration, and in this case both are having the same acceleration. It will be acted upon by a force N1, and this is M1G, and a friction will act F1. This is N2, this is M2G, and a friction will act F2, correct? So if I'm making the combined FBD of M1 and M2, combined FBD of M1 plus M2. So of course in this FBD, T2 will not appear, because for this FBD, T2 will be an internal force, and we can sum up both N1 and N2 and write them as a single force N, This is y-axis and this is x, and the system is having an acceleration w towards the x-axis. Now this will be m1 plus m2 times g, and this will be F1 force, frictional force on first block, and this will be F2, the frictional force on the second block. Now F1 will be, since we are assuming a kinetic model that the blocks are moving, so we'll use the formula for kinetic friction. So F1 will be mu, and in place of mu they are given the value of k into n1, and n1 is equal to m1g. So k m1g, and f2 will be, again it has a coefficient k n2, so it will be k m2g. Okay, now if, and one more force will act here, the tensional force. Which one? That is T1, the first string which is pulling this system. I'm making the combined FBD. I'm making a combined FBD of m1 and m2. So if you apply Newton's law on the x-axis, so I'll get net force on the x-axis will be T1 minus F1 minus F2, and AX is W. So apply Newton's second law on x-axis, sigma fx is max. So I will get the equation T1 minus F1 minus F2 is m1 plus m2 times W. So I will get, put the value of T1 in F1 and F2. So it will be kg m1 plus m2 will be equal to m1 plus m2 times W. Let it be equation number 3. Okay, so this is the equation again in T1 and W. Okay, so we got two equations. You can see equation number 1 and equation number 3. Both are in the parameters T1 and W, and our goal is to find W. Then only we can analyze whether the motion will take place or not. So from equation number 1, the mathematical goal is, from equation number 1 and equation number 3, we can eliminate T1. So what we can do, we can simply add equation 1 and 3. T1 will be eliminated, correct? So when you are adding 1 and 3, you will get the equation m naught g minus T1 plus T1 will get cancelled away, minus kg m1 plus m2 is equal to m1 plus m2 times of W, correct? So when you make W as the subject, so W will come to be, you can take G common, and you will get m naught minus k m1 plus m2 divided by m1 plus m2, and there is also, plus m naught W, that is from equation number 1 RHS, so plus m naught. So this is the value of G, and in this problem it is given m1 is equal to m2 is equal to m naught. It is given in the problem, all the three masses are equal for this problem. So in this special case, you can take m naught as common, say all you are taking as m naught. So m naught can be taken common, and you will get 1 minus 2k divided by 3 m naught. So m naught will get cancelled away, and W will come to be G 1 minus 2k divided by 3. So this is the value of W in terms of k. When you are assuming the motion is happening, when you are assuming that motion is happening, so the acceleration is coming to be G 1 minus 2k by 3. So when we are taking the model of motion, both these blocks are accelerating towards right with an acceleration W, and your m naught is accelerating downward with an acceleration W. So W is coming to be what? M naught 1 minus 2k divided by 3. W is coming to be G 1 minus 2k into 3. That is the value of W if you are assuming that motion is happening, correct? So this you got the value of W. Now the question arises whether the motion will take place or not. This is the assumption of the motion. What we did, we have taken a model in which we assumed that blocks are accelerating with an acceleration w, and w came to be g times 1 minus 2k by 3. Now the critical point is, in the problem it is being said consider all the cases. So we have to dig deeper, we have to go deeper and do some analysis whether motion will happen or not, right? So as I told you in the previous skill, when there is only one possible direction of acceleration, we can label A. If A comes to be positive, greater than 0, then the motion will happen. And if A comes to be negative or 0, the motion will not happen. So now we will do this analysis in this problem. So the next key point is, we will decide whether motion will take place or not. So we'll consider two cases. One, when the motion takes place, another, when the motion will not take place. So when motion will take place, so we will have the value of w as greater than 0, correct? We will have the value of w as greater than 0. And w came to be g 1 minus 2k divided by 3. So if motion is happening, I will get g 1 minus 2k divided by 3 as greater than 0. So you can apply the basic rules of inequality. So 1 minus 2k will be greater than 0. So we'll get 2k is less than 1. So we'll get k is what? Less than half. So if k has a value less than half, then only the blocks will accelerate. Here we got a concluding point. If k, the coefficient of friction, is less than half, if it is less than half, then only the blocks will have an acceleration. So we will see this case when the motion will take place. So it is the condition when k is less than half. And of course, we know k can't be negative. So the range of k will be between 0 and half. So motion will happen. And in this case, what will happen? Now you can find everything, correct? So this is your m0, this is your m1, this is your m2, and this is your w, this is your t1, and this is your t2. So in this case, the acceleration will come to be how much? G 1 minus 2k divided by 3. This is your A or W, first answer. This is the case when k has a value less than half, when the motion is happening. Now if we have to find what will be the value of T2, in this case, what will be the value of T2? So you can make the FBD, and friction will act kinetic friction on, because motion is happening. So this will be the kinetic friction. So make FBD of M2. So when you are making the FBD of M2, you will have N2, M2G. Here the kinetic friction will act F2, and this will have a force T2, and the common acceleration is W. So you can apply Newton's law. This is X, this is Y. So you'll get straightforward, I can say there is a vertical equilibrium. So N2 will be equal to M2G, and net force on the x-axis is T2 minus F2, and F2 is a kinetic friction, that is the coefficient of friction multiplied by N2. So K mg. So net force, the acceleration along the x-axis is W. So apply Newton's second law on the x-axis. So you will get T2 minus F2 is equal to M2 times of W. So you'll get T2 minus K M2G is M2 times of W, and W is what? G 1 minus 2K divided by 3, correct? So your T2 will come to be how much? You can take M2G common factor, and you'll get 1 minus 2K divided by 3 plus K. So you'll get T2 as M2G 1 minus 2K plus 3K divided by 3. So you'll get T2 is equal to M2G by 3, and here it will come to be 1 plus K. So this will be the value of T2 when motion is taking place. This is the value of T2 when motion is taking place. Okay. And when motion is taking place, the acceleration is this much. Already you got. And when motion will take place, when k is less than half. This is the first case, first possible case, depending on the value of k. when the motion will take place, correct? When the motion will take place. And if you want to write the complete range, since k can't be negative, so you can write greater than equal to 0 and less than half. So this case is applicable for this range of k. This complete analysis is applicable for this range of k. Got it? Now we'll go to the next case when the motion will not happen. So when the motion is happening, you got the value of acceleration, you got the value of T2, that is the tensional force in the interconnecting string M to G by 3, 1 plus K. And in place of M2, you can write M1 or M0, whatever, because all the three masses are equal. Now we will come to the second case when the motion will not happen. Now we'll see what will be the condition for this. So the value of W came to be G 1 minus 2K divided by 3. Now, if the motion will not happen, so going by the fundamentals, for no motion, W will be less than or equal to 0. So you will get G 1 minus 2K by 3 will be less than or equal to 0. So you'll get 1 minus 2K will be less than or equal to 0. So you'll get K is greater than or equal to half. So when K has a value in this problem, when coefficient of friction has a value greater than or equal to half, then the blocks will not move. Then the blocks will not move. Okay? This is the scenario when motion will not happen. So already we have seen when K is less than half, motion will happen. We got the value of A and tensional force. Now we are going when K is greater than or equal to half, then motion will not happen. Now let's see what will happen when there is no motion. When there is no motion, now there is further analysis, because now the friction acting will be static in nature, not the kinetic one. And static friction we all know is self-adjusting. So we have to do little bit of analysis. So see, this is your pulley, and this is mass M0, and this is M1, and this is M2. Now everything is static, correct? Everything is static, assuming that K is greater than or equal to half. So if everything is static, so first question arises. Say the tensional force in this case is T1. Now the first point of consideration is whether this string will have a tensional force or not. Now, if you see the fundamental which I covered in Newton's law, we have seen if something is like this, and this is a string, and you are pulling a block with a force F, then a frictional force will start acting. Okay, a frictional force will start acting if it's a rough surface. And of course, it's a static friction because the block is at rest. Now, since it is at rest, Fs equal to F. So when Fs is equal to F, this string will be sag. There is no tensional force in the string because friction is itself is sufficient in balancing F. If you are increasing F, the frictional force Fs will increase. So when you are increasing F, Fs will increase, and again Fs will balance capital F, and again T will be 0. But it will happen up to a certain limit. It will happen up to a certain limit. When your capital F exceeds Fs max, then what will happen? Now friction got the upper limit. Now it will act as Fs max. Now it cannot exceed beyond it. Now what will happen? This string will have T. Now T will be non-zero. It will become tight. Okay. Now along with Fs max, T will also start acting on this string towards right side, and T along with Fs max will be balancing F to keep the block at rest. These we have covered in the fundamental lectures, correct? So whether tensional force will act in this string or not, it depends whether the driving force is less than or equal to Fs max, or whether the driving force is greater than Fs max. Okay, so that is the fundamental which we will employ in this case. So same, since everything is static, since everything is static, so if you are making the FBD of m naught, so this is your T1 and this is m naught g, and it is at rest, so you'll get T1 is equal to m naught g. Correct? That's for sure. That is the settled equation. If it is at rest, and we are talking about the rest condition, then k is greater than or equal to half. Now, if you come to the FBD of m1, so m1 will have a force n1, T1 will act like this, m1g will act like this, and T1 is giving it a tendency. T1 is giving it a tendency for relative motion, so friction will oppose it. So friction will act here, say F1. Now the point is, if you consider this analysis, so can you think, will this string have tensional force? Will it have tensional force? Yes or no? So it will depend. If T1 exceeds F1 max, then only T will act, following this analysis. Till your T1 is less than or equal to F1 max, then F1 max or F1 itself is sufficient to balance T1. Till that time, this string will remain sag. Okay, so we'll see here also there will be two subcases. When the block is not moving, there will be two subcases of the second case. Okay, so we are doing case 1, case or say 2a, first case of second, so I'm giving it a name 2a. So I'm making the FBD of m1. So when I'm making the FBD of m1, it will be n1, it will be m1g, and this is your frictional force F1, and this is your T1. I'm not making T2, mind it. I'm not making T2. I'm assuming, I don't know, because T2 will come into play only when T1 will exceed F1 max. Okay, so let us see till when T2 will be 0. Till when T2 will be 0. Till when T2 will be 0. It will till T1 is less than equal to limiting friction of F1 max. And T1 is till m naught g is less than equal to k n1. That is till m naught g is less than equal to k, and what is n1? m1g, and g will get cancelled away, and moreover m0 and m1 are given to be equal. So it is still k is greater than or equal to 1. Okay, so we got case 2a. We got case 2a if k is greater than or equal to 1. Okay, if k is greater than or equal to 1, then what will happen? And don't think that k can't be greater than 1. Many students think the coefficient of friction will always be less than 1. No, that is not the fact. There are materials which have a coefficient of friction greater than 1. This we have covered in the fundamentals. Okay, so k can be greater than 1. So this is your m1 and this is your m2. And in this scenario, when k is greater than 1, T1 will act, but in this string, there is no tensional force. T2 will be 0. Now, no pulling force will act on M2. So it will have N2 and M2. And in this, the frictional force will also be 0 on M2. Correct? In this, the frictional, I'm doing the complete analysis. And on this block, the frictional force will also be 0 because there is no pulling force. On M1, a static friction will act like this, F1. A static friction will act F1. This is your N1, this is M1G, and this is your T1. And since it is at rest, so F1, the frictional force on M1 will be equal to T1, that is equal to M0G. So we got the complete analysis. When k is greater than or equal to 1, we got everything. Correct? When k is greater than or equal to 1, the acceleration of the block is 0, number 1. Number 2, your T1 is equal to m0g. T1 is equal to m0g. Number 3, the frictional force on first block is equal to T naught, that is M naught G. Number 4, the tensile force in the binding string is 0. And number 5, the frictional force in the second block is 0. And when it is happening, when K is greater than or equal to 1. Okay. Now let's see the second subcase of case 2. That was the first case when we were assuming T2 is equal to 0. Now we'll come to second case, case 2b. Now see what will be case 2b. Now of course we will assume that this T1 exceeds the value of F1 max, and T1, because everything is again static, that is the main case 2, that is simply the subset of case 2. So everything is static. So T1 in the static condition came to be M naught G. Now let us assume that when T1 is greater than F1 max, so when M naught G is greater than Kn1, that is when M naught G is greater than K, and what is M1? M1G, and M1 and M naught are equal, and G is also equal. So when K is basically less than 1, when K has a value less than 1. And for second case, we have seen for the second case, K is greater than or equal to half. So all the two subsets are the special cases of second case. So you can include this intersection in solution 2. So basically you are getting when K is less than 1 and greater than or equal to half, then this case will follow. When K is less than 1 and greater than or equal to half, then this case will follow. Now since T1 is greater than your Fs max, so here T2 will start acting. Okay, now T2 will start acting, and this is your what? N1, this is M1G, and now maximum frictional force will act because it has already reached its upper limit. Then only T2 will start acting. So this is your T2 and this is your T1. So if you make the FBD of first block, so you'll get, and since it is at rest, so you'll get T1 is equal to T2 plus F1 max, and T1 has a value of M naught G, and this is your T2, and Fs max is K multiplied by N1, that is M1G. So T2 will have a value, you can take M1 and M naught are same, so you can take M naught G common and you will get 1 minus K. So this came to be the value of T2. This came to be the value of T2. Now what will be the frictional force on M1? So F1, since it is acting at its uppermost limit, maximum limit, so F1 will be F1 max. So it will be K N1, that is K M1G. This is the frictional force on first block. Now if you come on the second block, so one normal force is acting, one M2G is acting. Now it is having a tendency, because now tensile force is acting on it, T2, and a frictional force will act on it, F2, which is again static. But this is not necessary that F2 will also have the maximum value. Here it got the maximum value because after attaining the maximum value only T2 will start acting, and it is also at rest. So your F2 will come to be T2. So frictional force on the second block, that is the static friction, will be again the value of T2 M naught G 1 minus K. So that is very beautiful problem. There's a lot to analyze. Okay, there are a lot of very fine hair-like concepts in this problem. So we have seen different cases. Okay. First of all, we have taken the model. I'm making a recap, a road line, what we did in the whole problem. First, we have seen the background. If we are making, there is only one possible direction of A. We can label that A. If A comes to be positive, motion will take place, and if A comes to be negative, motion will not take place. Then in this problem, at the very first place, we have assumed that motion is taking place with an acceleration of w, and of course gravity is acting downward, so w will be like this downward, and for this it would be leftward. And then we have made the FBDs, and since we have assumed a kinetic model, a motion model, so kinetic friction will act, and from the FBD we got the value of w, the acceleration g times 1 minus 2k by 3. Now the critical point arises whether the motion will actually take place or not. So there will be two branches radiating out. There will be two branches radiating out. If the motion takes place, then W will be greater than 0. And when you apply this inequality, you got the conclusion that K is less than half. K is less than half. So if the coefficient of friction is less than half, then only the motion will take place. One thing is clear. Now we will do the analysis for this model when K is less than half. So when K is less than half, the motion is actually taking place. And so the frictional forces acting will be the kinetic frictional forces. And we made the FBD, and already we got the value of W, and then we got the value of T2 by making the FBD, and we got everything. What will be the value of T2 in this case, and what will be the acceleration in this case when K is less than half. Then we have seen second case when the motion will not take place. So if the motion will not take place, then according to the standard convention, the acceleration must come to be less than or equal to 0. So this is giving you the value of K to be greater than or equal to half. Correct? It is giving you the value of K to be greater than or equal to half. So in this case, the motion will not take place. And when there is no motion, then the question arises. Now also now, there in the second case, in the second branch, there are further two sub branches. That is the beauty of the problem. In the second case, there are further two sub branches. If the motion is not taking place, the point is that whether this string will have a tightness or it will be loose, whether it will have a tensional force or it will not have a tensional force. So for that, I told you, we have covered this fundamental analysis. It depends on the pulling force, whether tensional force will act or not. So I made a recap of this fundamental analysis for the new students. Okay, if this is a pulling force and F is less than or equal to Fs, no tension will act on this string. But as soon as F exceeds Fs max limiting friction, the tensional force will start operating. So first we are assuming the case 2a, case 2a, when there is no tensional force in the second string. This will happen when T1 is less than or equal to F1 max. And this will happen when K is greater than or equal to 1, when the coefficient of friction is greater than or equal to 1. So when coefficient of friction is greater than or equal to 1, no T will act, this string will be loose. So N2 will be equal to M2G, no friction will act on M2. Here static friction will act, and the static friction will balance T1. So F1 will be equal to T1, M0G, and the acceleration will be 0. So all the points I've written here. Okay. Now we came to the case 2b. It is also the static case, but now T1 is greater than F1 max. That is, this string will become tight in this case because this driving force exceeds the limiting friction. So the tensional force will come into play along with your friction to balance that driving force. This will happen when K is less than 1. And of course, the whole case 2 has a condition K to be greater than or equal to half. So you superimpose both the condition. So for 2b, this K inequality of K comes K is greater than or equal to half and less than 1. So T2 will also act in this case when K has this range. And when you make the friction on M1, friction will be static and at its limiting value, because after exceeding the limiting value, only T2 will start acting. So this will be F1 max. And on M2, T2 will act and F2 will act, will be again a static friction, but may not be limiting value. So F2 will be equal to T2, and from FBD of 1, you can find T2. Okay. So this is IRODOV problem number 60, a very beautiful problem, giving you a lot of deep analysis in some very finer, or you can say deep concepts of Newton's law, friction, tendency of motion, whether the tensile force will act or do not act.